Welcome everyone. Thank you all for coming. We know that it is getting closer to midterm, so it's going to be a little bit more harder to attend meetings, but we appreciate you all being here and we expect this meeting to take approximately 1 hour. We hope you guys will gain as much knowledge from it as possible. Yep. All right, in today's meeting, we're going to be discussing a couple things. We're going to be talking a little bit about reinforcement learning, neural networks, classification algorithms, computer vision, and robotics and autonomous systems. If you guys have questions, please keep it till the end, and we're going to have a Q&A then, and we can really discuss it and also get to know you guys more then as well. So that's the plan for today's meeting. Okay, cool. So in this section, my partner Michael and I will be talking a little bit about what reinforcement learning is and how it's applied in certain projects today in the industry. So reinforcement learning, if you think about it, is on a high level, is essentially a branch of machine learning where you're able to train a system through an iterative process to learn from its mistakes. One of my favorite definitions for reinforcement learning is basically it's a type of dynamic programming that's able to train algorithms using a system of rewards and punishments. Basically, you're rewarding the system to learn from its mistakes. So there are some key factors you guys are going to be learning, or you guys are going to be hearing a lot within this part of the presentation, which include an agent, an environment, an action, and a reward. So what is an agent? An agent is an entity or a representation of the system that you will be training towards the entirety of the process. Basically, the agent's objective is to achieve an intended goal by interacting with an environment and to maximize the agent's overall reward. So the environment is basically the state space or the surroundings of the agent, where the agent will be interacting in order to achieve a specific goal. The agent is going to be taking an action, basically making a decision on what to do in response to a sudden change in the environment, also known as a state. This action is guided by a strategy referred to as a policy, where essentially the objective is to identify the best path or the optimal path to achieve the greatest number of points possible. The points are represented through a reward. So the reward is basically a measure of the desirability of the action and is returned by the environment. So essentially, an easy way to think about this is for every correct action taken or for every correct decision made, the agent will be awarded a point. But for every action that has been incorrectly taken or for every wrong action, it'll be penalized a point. So the whole point is that through every iteration, the agent's going to look at the optimal path and look at all the previous decisions made and basically identify the path to achieve the greatest number of points, the greatest sum of points. So the end goal is basically for the agent to learn the optimal policy in the environment to achieve the greatest reward, like I mentioned before. The key thing to remember is that it is an iterative learning process, so it takes a very long time to train your agent, especially on the complexity of the environment and how large the state space is. So you want to just really make sure that with the actions you program your agent, you really provide it with as much information and attributes in terms of analyzing what it should do and how it should react with sudden change in the state. Moving forward. So current RL applications.
So some of the current reinforcement learning applications systems uses reinforcement learning to suggest users what content they might find most useful and give some random but relevant content to explore a new interest. So the data is prepared in a way such that the content, when viewed by the user, or is taken as a state, and the next content seen by the user is the action, and the reward can be formulated by either based on the user interaction time or by a review, or if a user purchased it, in the case of like online shopping. And recommended systems can also be built around various reinforcement learning algorithms like actor critic, Q-learning, DDPG, or temporal learning. And another reinforcement learning application is data center cooling. So in this scenario, reinforcement learning is utilized to achieve optimal cooling for data centers while trying to minimize the use of energy. So this is done by separating the system into controls, states, and disturbances, where the controls are the variables that can be manipulated. So these include like things like the fan speed, which control the airflow, and the valve openings, which regulates the amount of water used to cool for each air handling unit. And the states are basically used to collect the process variables, which we wish to predict and regulate. So these include the differential air pressure and the cold aisle temperature. So the system will consider it a reward if those two are maintained at a desired constant rate. And lastly are the disturbances, which are the events and conditions which we cannot manipulate or control, but they still have an effect on the conditions inside, like the server floor. And so these include things like server power usage, which serves as a representation for the amount of generated heat, as well as the entering water temperature of the chilled water measured at each air handling unit. So with all of these subsystems working together, it's possible to cool a dating center through model predictive reinforcement learning. So a lot of the reinforcement learning is popularized in top tier tech companies like FANG, which include Facebook, Amazon, Netflix, and Google. And so in the case of Amazon, while other competitors, like their recommendation system, how they work is that they exist in only one aspect of the customer journey, for example, like a list of related items on the site checkout page. But Amazon has integrated many recommendation entry points into online experience to maximize their cart value. So as a result of that, their consumer purchases on Amazon, 35% just strictly come from the recommendations. Another company that uses reinforcement learning is Netflix. So Netflix uses reinforcement learning to help shape its catalog of movies and TV shows by learning characteristics that make the content successful. So they use it to optimize the production of original movies and TV shows in Netflix's rapidly growing studio, which I don't understand why cuties is a thing, but apparently that's one of the reinforcement learning popped up. But yeah. And then lastly is Google. They use AlphaGo, which is the same agent that beat the world champion of Go, which is just a game, to figure out the best framework of cooling infrastructure like fans and ventilation. So it will effectively lower energy consumption. So AlphaGo suggests options to improve energy efficiency to infrastructure operators. So this resulted in a cut of like 40% of the energy needed for Google's cooling data centers, which, as you can imagine, is like a lot of savings in the overall cost.
Cool. So now we're just going to talk a little bit about some reinforcement learning projects. So in this first image right here, this is actually one of the projects that I personally have worked on. It's called the telemedicine robot. So for my capstone project, I actually had the opportunity to work with AWS, and we were in charge of designing a robot that's capable of transporting medication to different rooms within the ICU of a hospital. Essentially, our pain point that we're trying to tackle is that now that with the pandemic occurring, doctors and nurses are expending much of their mental and physical energy in trying to fight the disease and help treat patients. Essentially, they're facing exhaustion, and that's something that's definitely slowing down the process. So our solution was to develop an autonomous vehicle that's capable of delivering these medical supplies and resources to different rooms within the ICU so that the doctors and nurses can tend to the patients and conserve their energy there. Essentially, here you can see that we programmed our agent. In this case, is represented by the AWS Deep Racer, which is the name of our robot. And this is through our simulation. Currently in Capstone 2, we're focusing on our implementation stages onto the actual robot. And the training process is, like I mentioned before, taking quite some time. So essentially in the simulation, you see the Deep Racer on a virtual track, which is essentially what we try to implement into the hospital by developing another track. And this Deep Racer, we programmed it so it get for lane detection and obstacle avoidance. So whenever our agent views the white lanes through a 4-megapixel camera, it's going to make sure that it stays within it. And if it's going to start by failing initially quite a bit. If it exceeds out of those lanes, then it's going to lose a point. But if it stays within those lanes, it gains a point. That's how we programmed it with our reward function. Same concept with the objects. Any incoming objects it avoids, it's awarded a point, but any objects it hits, it's penalized a point. And this process is iterated as many times until we achieve a high enough accuracy to make sure that it can be successfully deployed onto the physical model itself.
Yeah. And another project that deals with reinforcement learning is like a tic-tac-toe bot. And it uses something called a Markov decision process, which is basically just a mathematical model that uses Markov chains. And this contains, obviously, you got the the state set, which is where the state set of one player contains all the boards when it's his or her turn to play. So in our case, the state set contains all the boards that have the same number of X's and O's. So like, for example, the empty board is in the state set. And in addition, all the boards when the game is over are also in the state set, and they are called end states. Another thing that's in this project would be the action set, which contains all the options of, for example, player X to play. That is all the numbers in a specific state. And there's also a probability function where one player takes an action and the environment responds and returns a new state after the other player's turn. And every possible state has its own probability. So the goal is to find a function that maps a state to the best action or optimized path one player can take. And finally, there's the rewards, where we can define that as 1 if the player assigned to X 1, or -1 if the player assigned to O's 1, 0.5 if it's a tie, and 0 otherwise. So from this Markov decision process, the algorithm is able to optimize the strategy in order to win as many times as possible. And yeah, so with that, I'll hand it over to our next speakers.
Hi, so I'm Ava. I'm just going to be talking a little bit about neural networks, and kind of how they work in a few applications. And then my partner Jay is going to talk a little bit more about how they're used in computer vision. So basically, I'll start. So what are neural networks? They are patterns upon patterns. They break down images and words into pieces or neurons to learn and process what it sees. It refines upon each hidden layer, which you can see in the picture below, but I'm going to explain kind of what a hidden layer is later on. And then it produces output with the ability to correct itself, which is a huge component of why these are so important and why they're so useful. And so backpropagation, that's kind of what I was hinting at. That is kind of the ability to correct and go back and forth when there's an error made. So like it says there, it allows the networks to adjust the hidden layers when the outcome isn't right. And so like an example of that would be basically if you were trying to classify something as, say, a dog, and it classified it as a cat, that would be wrong, obviously. And so it could go back and adjust. And so that's the picture right there that kind of explains that. And so in the green would be the hidden error values, and then it would kind of go back and adjust and keep going back and forth, until it's down. And so the general steps of backpropagation are calculating the error. And so how far is the model output from the intended output, which is pretty self-explanatory. Then you want the minimum error. So you want to check whether the error is minimized or not. And then you want to update the parameters. And if the error is huge, then you want to update the parameters, and check the error, repeat the process until the error becomes minimum. And then at that point, the model is ready to make a prediction and kind of decide what it wants to classify as. So there's a lot of different types, but two of the most important types of neural networks are feed-forward neural networks and recurrent neural networks. And so feed-forward neural networks is where information just travels in one direction from the input to the output. And then there's the recurrent neural networks where data flows in multiple directions. And then these neural networks possess greater learning abilities for more complex tasks, such as learning handwriting or language recognition, which makes sense because with the ability to go back and forth and adjust and learn kind of from what was wrong. There's a lot more many things you can do. English is hard. And so basically you can see in the bottom picture, that's kind of explaining how it goes right from the input to the output. There isn't really any back and forth, lot less going on. And then the bidirectional neural network at the top, that one's basically kind of has a representation of how it could go back and forth, and kind of just learn and see and adjust based on error. So the MNIST data set, so that's kind of what you're looking at with the numbers right there. And so it's used for number recognition. That's just the size of it. And so basically it uses hidden layers to break down parts. Did my audio just get messed up?
Yeah, just,
Yeah, there's an echo.
a little bit of an echo.
Should I leave and come back?
Yeah.
It wouldn't be an AI club without a robot, right?
Yeah, I mean, if anything, it really serves your purpose, like our purpose. Like it contributes to this whole presentation. So,
Is this better?
Unmuting and then can
Is this better?
yeah, it's better.
Yeah.
You got it.
Okay. So sorry, guys. I was hoping that wouldn't happen, but I have many issues with my mic. Anyway, so back to what I was saying. So we're on the MNIST data set. So it uses the hidden layers to break down the parts and pieces of the numbers. And so it's trying to recognize any version of the number. So it's able to detect it in any kind of form or shape. And so it uses the light and dark spaces and that contrast to kind of tell what part of the number and like where and like everything like that. And so it calculates how much white, how much black, and where it is. And then that's kind of how it's used to determine the number. And so it uses the neural networks to kind of keep learning and keep going back and forth to see, did it get the right number? Did it not? That whole thing. And so basically then there's another picture of how a deep neural network would be seeing things. And so it's a picture of an Audi, and then it kind of shows how there'd be the black and white, like contrast those images, and then it would kind of compare it to what it knows already, and then to make its final prediction of the right car. So some applications of where neural networks can be used. Honestly, they can be used pretty much in anything you want. So you can use them for recommendations. Cars can drive autonomously. You can make more realistic CGI faces, machine translation, fraud detection, all those good things. And so what is on the screen is kind of an example of a recommendation application. And so here it's making book recommendations based on similarities in books and words and all that. And so it's just showing a plot of that. And then it's like what it's most linked to in Wikipedia, what's most similar in like which direction for all different books and stuff. So yeah, so it can be used pretty much anywhere. It's pretty easily moved and translated into different applications, but it's really cool and really important. But yeah, so that's kind of a breakdown of what neural networks are. So now I'm going to pass it along to Jay, and he's going to talk about computer vision.
Awesome. Thanks a lot, Eva. Yeah, I'll be talking more about the application of neural networks, and one of the classic applications of neural networks is computer vision. And to define computer vision itself is a task, because most of the definitions of computer vision differ from applications to applications. So if we are referring to a classic image, it normally entails to understanding what really that image means in terms of computer language. And if we are talking in terms of robotics, it normally really translates into understanding what the sensor modality means and what do we really mean to achieve. And it is also one of the earliest definitions of computer vision was termed along the lines of inverse of computer graphics, where typically in terms of computer graphics, we normally have a model and we create images or graphics out of that particular model. But what computer vision itself does is it takes images and creates a model out of those things. So How do I change? Yeah. Yeah. So few of the disciplines that are closely related to computer vision are the following ones, and normally most of these deep learning applications target along image processing, scientific medical imaging, computer graphics, learning based models, artificial intelligence, and most of these visual neuroscience applications. And to typically understand why computer vision is really tough is to because if you understand what pixels are basically set of values and basically matrix of values, and to understand what really picture is to understand how human perception works, because how we humans see images is when we look at this image we can normally classify that hey, I see a house, I see trees, I see cars, and I see maybe a set of cars, not just one car. But to computer this is really tough because all it sees is just a matrix of values. So computer vision really classifies this particular perception problem into a mathematical version which can answer questions: what kind of scene this is, where are the cars, how many cars do I see, or how far the building is. And this is what we term as the conceptual knowledge or context of particular image. And why really computer vision matters, and I have listed for few of these 6 applications which I think are the broadest classification of where computer vision really lies. Is first being safety. We know a lot of self-driving cars really entail around how accidents can be prevented, where human errors are really prone to be there. Health systems, medical imaging, a lot of cancers and tumors are really solved where radiologists might would have given up, and there have been some very successful tasks where medical imaging really proves better. Security, we see cameras everywhere in convenience stores and everywhere, and they are used for security purposes for face recognitions. Comforts, where a lot of robots who can help people who are paralyzed or who cannot be physically active when they should be. Comfort based models are really present over there. Fun, we use a lot of AR VR stuff that is coming out, and it uses computer vision on its very depth. And access, we see a lot of particular information on Google and other database services which really requires to understand what this image is and how to classify them. So few of the typical applications that really stood out in the earlier times was this vision-based biometrics, where this is a particular application where an Afghan girl who was reportedly missing few years back, and later in one of the government scans, a woman who was later scanned by the government was found, like she was found to be the same older person who was same older girl who was found back in the reigns of I mean she was found in some other country, I don't remember the exact details, but she was reunited with her family just based on iris classifications. So these kind of vision based biometrics have really proved significant, and they are not just academic or research based application, but they are used in real world applications. A lot of animated movies use these kind of special motion capture techniques, which use computer vision techniques to interpolate or extrapolate an animated technique. And few of the high stake applications like medical imaging, probably few of the biggest applications in terms of revenues and in terms of interest from academia and research has been medical imaging, because a lot of diseases like long-term diseases or like cancer, tumors, Alzheimer's, migraine, they seem to have a saturation point from a medical perspective, where biomarker discovery is really tough for a human or any radiology or any medical expert to really find. But computer vision have been really critical into understanding where these diseases lie and how we can create drugs to prevent them. So this is a classic application that I worked last year based on computer vision techniques, where if you can see this GIF where I'm standing in front of a high quality video which is not compressed, and just based on non-contact methods it is trying to calculate my breathing rate and my pulse rate. And the way how it does is, if you can see a small video that is on the top of this particular GIF, it shows a region of interest in a rectangular format, and basically it tries to see the variations in my veins. That is normally how we as radiologists normally calculates the breathing rate and pulse rates. And these are these but this particular application was highly rated because it was matching how the contact based methods were really present. But a classic application of this particular computer vision technique was to be used in neonatal cares, where children who are born with deficiencies who cannot be treated due to skin malnourishments, they cannot be touched, and contact based methods are really struggling over there. So these kind of techniques can be used in order to monitor their vitals and get the necessary uh, requirements of a doctor to proceed with the treatment. So computer vision has really bright applications. A lot of like Eva mentioned, a lot of application of computer vision comes from neural networks, and neural networks are a backbone of computer vision applications. So yeah, that's all from my end from computer vision. Next we have classification algorithms.
Okay, thanks, Jay. So I'll just go through. Me and Karthik will go through the classifications and its uses. So what is a classification problem? So it's basically classifying different categories of or classes. So something like classifying different kinds of fruits, or cancer prediction, where it's like whether a patient excuse me, whether a patient has a cancer or not. Fraud detection, which is used by banks. So a few types of I've just broadly classified this into like binary, multi-class, and imbalance. So we'll see those with examples in the next slide. So the one shown in the figure is a multi-class, which has like different labels of 0, 1, and 2, and they're like classified based on different features. So features can be anything. Basically, if we're classifying fruits, we can say the size of the fruit, what color it is, how much does it weigh. So those are all the features, and based on them, we classify them. So yeah. So here are few of use cases. So email spam detection, customer churn prediction are types of binary classification. Customer churn prediction is like where a company wants to know which customers might stop using their service, like banks or like some streaming services like Netflix. So that's what they use these algorithms for. And then multi-class classifications can be optical character recognition, like recognizing characters, and then different kinds of fruits or anything like can be used along with computer vision. And then imbalance classification is like fraud detection, cancer detection. These are also binary classification, but the only difference is like uh, the occurrences in one class is more than the other, like cancer. So maybe 99 out of 100 people won't have cancer. So there's an imbalance between the occurrence of different classes. So that's why they are like classified differently. And we would be having mm, workshop on customer churn prediction next month. So we'll keep you guys posted. And there are these are the basic algorithms like logistics, SVM, decision trees, random forest, gradient boosting, and we will be going to some of this. And I think Karthik, my friend Karthik, will explain you about the basic one, which is logistic.
All right. So every one of us, like we know about the linear regression model, which is based upon this equation called y equals to mx plus c. So x here is the independent variable and y is the dependent variable because it is dependent upon that x basically. So linear regression is one of the most simple machine learning algorithm, which is based upon the supervised learning. And supervised learning is something, like when the algorithm learns upon the labeled data set. And an unsupervised model is when the model tries to predict based upon the features, basically. So in the linear regression, the output is always continuous. So we cannot get the zero and one or zero or one probability or yes or no classification because linear regression will always give us a continuous output. So this is the specific reason that we switch to logistic regression for the classification problem. So as you can see in the image right now, so this is a linear regression model, and you can see that there are like a lot of misclassifications. You can see like two zeros on in place of the red nodes, which should be actually one. So this shows that linear regression is not good for the classification purposes. So if you could go to the next slide. Yeah. So that is the reason we switched to this model called logistic regression. So as you can see, this S-shaped curve in the graph, this is basically the logistic model, or the S curve we call it. So this is called the sigmoid function, which I'll be talking about later on as well. So logistic regression is basically a statistical method to predict binary classes, meaning that it will give you the output as 0 or 1, or maybe yes or no, which is the required output for the classification algorithm. So that is why logistic regression is specifically used for classification purposes. And there are some properties of the actually you can go back. So there are some properties of the logistic regression. So the dependent variable, which is the output, or y, it follows the Bernoulli distribution, and the and also the estimation is done through the maximum likelihood method, which is also another kind of algorithm basically. So the types of logistic regression is binary logistic regression, multinomial logistic regression, and the ordinal logistic regression. So binary logistic regression is where when the output variable or the target variable will have only two possible outcomes, such as yes or no, or maybe spam or not spam in the case of email spam that Rishabh talked about. And in the case of multinomial logistic regression, the target variable can have three or more categories, and for the ordinal logistic, the output categories could range from more than three. So like the restaurant rating that goes from 1 to 5. So this is the S-shaped function I was talking about in the previous slide. This is called the sigmoid function. The sigmoid function is represented by this equation called y equals to 1 upon 1 plus e raised to power minus x. And this function will definitely help categorize the previous example, as I showed before in the previous slide, for the cancer patients. So this sigmoid function, which looks like an S, it will always map the output value to 0 or 1. And if this curve basically goes to the positive infinity, the output will always be 1, and if it goes to the negative infinity, the output will be 0. This is because we define it in a way that anything above 0.5 would be classified as 1 or yes, or anything below 0.5 would be classified as 0 or no, basically. That's it. And this is the basic syntax for the logistic regression. So one of the good things about this logistic regression is that there's a sklearn library in Python, which has the logistic regression library inside that. So we can just basically import that and directly use that. So here you can see that we basically import the class, then we create the instance of the class with these two parameters that are required, and then we are just fitting that on the train data, and then we can predict it using the model.
Okay, so this is just a overview of how a decision tree works. So an employee has got an offer, so he wants to decide whether he wants to accept the offer or not. So these are the various features. So he basically we go through the features, and then in the end we get the result. So just like, is the salary less than 50,000? So if it's yes, then he declines the offer. If the salary is greater and he sees the like various parameters of commute and whether he gets free coffee or not, the free perks, so based on that he accepts or declines the offer. A similar thing can be like for classifying fruits, can be what's the color of a fruit. Suppose the color is orange, and then how much does it weigh? Like more than 2 pounds? Okay, then it might be a pumpkin. Anyways, I just told pumpkin because Halloween's coming. So this is how it works. So this is a decision tree, and then random forest is basically group of decision trees, can be 100 or 200, whatever. And then every tree uh, can get a different value, and then they all vote, and then like the majority of what the decision tree votes for, that is the output of a random forest. So random forest is just a group of decision trees. So all the algorithms that we discuss, we would be covering them in the hands-on workshops in the coming sessions. So yeah, that's it about the classification. So now my teammates Joshua and Jamie will take over.
Wonderful. Thanks. So my name is Joshua, and I will start this. I'll start this section on robotics and autonomous systems. So, to get started with robotics, it's important to take a quick look at the history of robots and automatons. Now that we discussed about reinforcement learning, neural networks, and other fields of AI, it's a good point to take a step back and kind of see where this all began, and how we came to the place we are today. So we'll start off by talking a little bit about the mythology of robots, how we can find this in Homer, in ancient Chinese literature, and other ancient civilizations, and then we'll talk about a few of the early robots and automatons that we can find in history. So we'll start off by talking about robots in mythology. This is not a comprehensive list of the books and stories that you can find the concept of robots discussed in, but these are the biggest ones and probably the most famous ones that you might encounter. So we'll start off with ancient Greece and Homer. If you've read the Iliad, you'll probably recall that there is a portion of the Iliad where they talk about automatons and essentially giving them human voices and giving them the ability to perform tasks based upon humans. You will probably remember that Daedalus, who is the person with the wax wings who flew too close to the sun, he forms instruments of labor, essentially servants that are completely robotic, completely mechanical, and they're powered by divine will. Nowadays, our automatons are powered by artificial intelligence, but it's interesting that thousands of years ago, the concept of a mechanical robot that would accompany you in tasks was discussed and actually written down in books like the Iliad. If you go to ancient China, you will actually see a similar concept in the book Liezi, which is a compilation of Taoist texts. You will see in chapter 5 of that book that there is a craftsman, Master Yan, who develops an automaton that is presented to a king, and the automaton is actually modeled upon the human body, modeled upon the organs, and it's essentially modeled in a manner that allows the automaton to perform all the functions of an actual human. We also see a similar concept of robots in Indian literature in the book Loka Panati in the 11th century. It talks about the Emperor Ashoka, who hears about automatons and finds their chief engineer, finds the person who designed these things, and essentially commands a large army of automated warriors. The interesting thing about this book and about the Indian literature related to robots is that they actually discuss about the ethics of artificial intelligence. You can actually read the book, and it talks about the fear of losing control of artificial beings. What happens when you have an army of soldiers that you cannot control? Which is, again, an interesting thing to see that people were discussing this about 1,000 years ago. We're discussing this today. The Terminator movies are great examples about what can go wrong if artificial intelligence goes out of control. But again, these are concepts that were discussed centuries ago, in some cases millennia ago, and it's something that we are rediscovering today as we make these incredible advances in artificial intelligence. Also in European legend, you will hear about brazen heads, very similar to the mirror on the wall in Snow White. These were essentially automatons on the wall that would answer questions that people would ask them, essentially an ancient version of Siri. But again, in mythology across the centuries, across millennia, you can see that people have always thought about the concept of having mechanical robots do tasks for humans. And it's a great foundation point to actually seeing how this got converted into into the physical world. So the next slide, we'll talk about early automatons across different civilizations. So we'll start off in China. One of the first recorded automatons is actually found in China in the 10th century BC by an artisan named Yan Shi, who made automata that could sing and dance. One of the automatons that we actually have descriptions of is the Cosmic Engine Clock Tower, built in 1088. You can actually see a description, an image of the clock tower on the left-hand side. This was one of the most complex mechanical mannequins that has been found, and essentially it was a 33-foot tall tower that chimed hours, ringed gongs and bells, and had little people come out every so often to entertain guests. We see something similar in Greece in the 4th century BC. We see Archytas, who developed a mechanical steam bird, essentially a mechanical steam rocket. You filled it up with water, put it over the fire, and a bird would actually fly with the power generated by the steam. You also see in ancient Greece Aristotle talk about the ideas of robots and how we can harness the energy of the wind and of the sea to power devices that could actually benefit humans. So in both of these images, both in China and ancient Greece, you can see people start to apply these concepts that we saw in mythology and convert it into physical devices. Moving forward, we go to the Arabian Peninsula, where we see Arabic water clocks. I apologize, there's a little text box that's peeking out from behind the photo. But we talk about Arabic water clocks and Arabic engineers. One of the most famous engineers was called Al-Jazari, who specialized in hydro-powered automatons. In fact, you can see a replica on the left side. It was one of his peacocks that would move around depending on the amount of water that you put in. Essentially one of the first hydro-powered devices that we know of. And on the right side, you can see an automaton that was developed by Da Vinci. It was a mechanical knight that was replicated upon the human body. You can see the inner workings of the knight in the acrylic case as well. But again, one of the first times we see people convert these concepts of brazen heads, of mythology, into physical devices that actually perform tasks for humans. Moving forward, we actually see this concept grow in Japan, where Tanaka Hisashige, who is considered to be the Thomas Edison of Japan, develops what are called karakuri automatons. You can actually see videos of these on YouTube, but these are small automatons that you could wind up, and these would do things such as fill tea for you. Some of them would even draw, write out letters, and some of them would fire arrows from a quiver. So over the past few centuries, like in the late 1800s, we start seeing more complex automatons that start actually helping humans. So for example, we see the robot serving tea to people starting to actually perform tasks that benefit people. And then on the right side, we see Tesla's submarine, which is actually one of the first radio-controlled systems. At the turn of the 19th century, this was developed in 1898, which is, again, one of the culminations of this entire concept of artificial intelligence. It was one of the first RC-controlled systems. It was designed to be a torpedo, but Tesla envisioned a day and age where they could put an artificial brain in there that could drive itself. So essentially, all the way from ancient Greece, ancient China, till the 1900s, there's this slow but sure development of robots and autonomous systems from a concept that was powered by a divine energy to a more physical representation and physical devices that started benefiting humanity. And then we go to the 1900s, and in just 100 years, we see incredible advancements. Could you go to the next slide? Thank you. So on the left-hand side, we see The Wonderful Wizard of Oz, which was written in 1900 by L. Frank Baum, one of the first introductions of robots into society, with the Tin Woodman, who is a cyborg. If you read Ozma of Oz 7 years later, he also talks about the Copper Man, Tick-Tock, who is another robot that was introduced into popular culture. But again, in the 1900s, in just 100 years, we see this incredible advancement. We see Electro, the second image, a giant 7-foot-tall robot built by Westinghouse, presented at the World's Fair. You can see his little dog Sparko at the bottom as well. This is one of the first times that robots were presented to the general public. Electro could walk, he could speak 700 words, and smoke cigarettes. And then moving forward, we start seeing robots and autonomous systems enter the workforce. We see the Puma robots, the third image, which quickly took over manufacturing tasks in robots took over manufacturing tasks in automotive facilities and in facilities that develop military equipment. And then late in the 1900s, we see autonomous robots come to the point where they are implemented into weapons, into missiles that can travel across the world and attack any target with incredible accuracy. And then finally, we see the introduction of autonomous systems into the medical sector with the CyberKnife system, one of the first robotic radiation therapy devices that brought technology into the medical field and allowed for incredible imaging to be done of the human body. So in less than 100 years, we go from the introduction of a cyborg character to actually developing a robot that can help in the healthcare sector. We go from electro to developing a weapon that can target locations from halfway across the world, which leads to the question, where are we now today with robotics and autonomous systems? And to answer that, I will turn it over to Jamie.
Hi, so you just heard of the history of robotics. So now the modern applications and what we have as of right now. So to start is something you've probably seen if you've been on campus is Starship at ASU, which are these little bots over here that go around and deliver food. But they're surprisingly very accurate with how they cross the street and they avoid people, they avoid other robots, they pay attention to the traffic lights. So the way they do that is they use cameras, GPS, inertial measurements, and ultrasonics to essentially judge the environment around them and then make their own judgments of how to adjust their movement. So these can include visuals as well as even have like a smell sensor to know what type of material it's on and other features like that. So in terms of manufacturing, they're also used in the supply chain. So this significantly decreases error, time, and injury that would be caused by human workers. And it consequently increases efficiency, safety, and customer satisfaction. And that last part is actually really important about the customer satisfaction because unlike humans who can make a bunch of errors and say have a percentage of like 1 per 5 items has an issue that they have to go back, robots can kind of have a perfect fulfillment rate where everything can be manufactured, packaged, and shipped out in a really timely, efficient order without having anything to go back on or any kinks in the process. And so they also can perform mundane and repetitive tasks that humans don't necessarily want to do or need to do or should be doing. And then they can go and do something that requires more of a human-centered versus robots, which can do these repetitive little things. So then another topic is weaponry, which brings into moral and ethical issues of applying robots in that way. But so they can use cameras and target tracking software like on tanks to detect where and when to fire, either at other tanks, other robots, or people. So then that brings into the moral and ethical issues of essentially allowing a machine with that artificial intelligence to be able to decide, should I shoot at this person and have the ability to take someone's life based off of an algorithm and doesn't have necessarily the moral abilities of a normal like soldier in that field. So that brings up that issue. Next slide, please. Okay, so how does it actually work? So there's kind of 3 major steps that it breaks down to. So the first is perception. So some robots on the simpler side use infrared and ultrasound sensors, but other ones have a 2-camera approach using stereo vision that gives them the ability to have a depth perception and image recognition software, similar to the robots that we just showed on the last slide. And then with those perceptions of the environment, what's around them, what they should do, they make these decisions. And then those decisions, those logical decisions that actuate into movements and physical actions of what they should do with their surroundings.
All right, hello everyone. My name is James. I'll be introducing you to natural language processing. I hope you're all still awake. So as children, we We were sheltered from things like having to do taxes and pulling all-nighters to cram for back-to-back finals. And also, we learned language through observing the environment, piecing together the rules and meanings of grammar like the Lego sets we start building but never quite finish. Similarly, natural language processing, or as I will refer to as NLP for short, extracts sense and learns from continued exposure to human language. Explained generally, it does this by parcelling sentences down to components such as syntax and semantics, and develops relations between these components. Machine learning in NLP is required as a set of possible valid sentences is countably infinite, impossible to just store in some database. But through these relations and a dictionary, we can train a model to generate and understand human language. Now, there's two fundamental techniques at the core of many NLP systems. Two S words that are part of each and every language as well. Words we also have happened to just send are on this PowerPoint. Will someone please take a guess to what they are? All right, cold room. We'll offer an instant promotion to anyone who speaks. Okay, I tried. Syntax and semantic analysis. Syntax, of course, dictating structure, while semantics meaning. Next slide, please. So, syntactic analysis. Here we have a basic parse tree. I've also written some production rules based off said tree. Before you ask, these rules are not written in Chomsky normal form, so for all the CS students. From the first rule, we see that a sentence in this language is comprised of a noun phrase followed by a verb phrase and an optional second noun phrase if we're feeling smart. The second rule declares that each noun phrase is comprised of an optional adjective and the noun or an optional adjective and another noun phrase. The last rule dictates that a verb phrase is a verb trailed by an optional adverb or proposition. Side note, the parentheses here represent optional as opposed to the asterisk I'm sure many of you CS folk are used to seeing. Since the second rule permits the creation of recursively long phrases, we can generate something like colorless green ideas sleep furiously. Please keep this sentence in mind. Now, can you tell me if, say, a sentence, androids dream of electric sheep, is valid? Excellent, that is correct, it is. You are all so smart. With these rules, we generate the grammar structure of a language. Grammar is being formally written as a for tuple with V being the set of non-terminals, T the terminals, P the production rules as written above, and S the star string. Now to you CS folk, you will also master this concept in CSE 355 or fail trying. All right, so you can see how we can make a structural sound sentence in English with these rules. But can anyone here tell me what colorless green ideas sleep furiously actually means? Well, we have a degree of ambiguity with a sentence, and it's not supposed to make direct sense. After we create a structurally sound sentence, we now have to make sense of it, and that's the hard part in natural language processing. Next slide, please. Semantic analysis. Apart from some exceptions, people are intelligent systems, smart enough to correlate context with the meaning of a sentence. There's many forms of ambiguity. Say, take the word base, for example. If I were to ask you, what is base? What would you most likely reply? If I were to type into a chatbot, what is base? It doesn't know if I'm talking about the base that you fish or the base that you can drop, like I saw. A method of removing abstraction is by drawing relations. Going back to the word base, we can instead say, what is the base clef? That leaves no confusion in what I'm looking for. Or we can say how to fillet a bass, which would infer that it is the right bass for the context. Finding meaning through context is called word sense disambiguation. We can use memory-based learning, a supervised machine learning method, commonly used for this process. By providing a set of tags which define items in a string and pre-tag strings before feeding actual data into generating a result, we can refine accuracy over time. This is just an initial glimpse at a part of speech tagger, which we will detail further in the next section presented by my lovely comrade Ashwarya.
Thank you, James. So, as James said, I will be talking about parts of speech tagging, but I will also be talking about some main subtasks in NLP, and they would be tokenization, parts of speech tagging, text classification, as well as information extraction. So to start off with, the first one is tokenization, and this is one of the most essential subtasks in NLP. So without doing tokenization, we most probably can't move forward. So given here is a basic high-level definition. So it's a way of separating pieces of text into smaller units called tokens. And here tokens can be words, characters, or subwords. For example, there's an example given here called customer service couldn't be better. So each word is classified as a token, and even the exclamation point is also, it's a character, but then it is also classified as a token. Basically, this helps us in understanding text because text is unorganized, and by tokenizing it, we are then able to perform different functions on it. Like we can have machine learning algorithms being run on the text input, etc. Another subtask which is very important is parts of speech tagging or POS tagging. In this, we break down a sentence into a list of words or features with a tag attached to each word. And it may be defined as a process of assigning one of the parts of speech to a given word. So one of the most, so for parts of speech, we have nouns, verbs, adverbs, adjectives, propositions, etc. So we would be taking a sentence. Once we've tokenized it, we would assign a part of speech tag to each token. You can take the same example above where you have customer service could not be better. So here, customer service would be a noun, could is a verb, not is an adverb, be is again a verb, better is an adjective, and the exclamation point is a punctuation. So a POS tagging is useful for identifying relationships between the words, and therefore it helps us understand the meaning of the sentences. Next slide, please. Now we have text classification and information extraction. Text classification is the process of assigning tags or categories to the text according to its content. One of the officers is actually going to talk about a project that he implemented based on this. So he'll go into further on that. But for now, we have unorganized text, or we might have several articles, and text classification can be used to identify which article is talking about which topic. So topic labeling would be one such use. Then you can even have sentiment analysis, which lets you know if a particular article is being positive or negative, or type of sentiment it's trying to convey. You can also use text classification in machine learning algorithms for spam detection and also for intent detection. The next subtask is information extraction. And on a high level, information extraction refers to the automatic extraction of structured information, such as entities, the relationship between these entities, and then attributes that describe the entities from whatever unstructured source we have. An example of this would be Aishwarya studies at ASU. Aishwarya would be one entity, ASU would be the other, and studies is the relationship between these two entities. So it gives you more information on the unstructured text. So the example that I gave you is also called name entity recognition. Another example of information extraction is keyword extraction. So this keyword extraction can be used to identify the main keyword in an article. For example, we can have an article on football or maybe even baseball. And so by extracting the keyword football, we'll be able to identify what is the main purpose of the article or what the article is actually talking about. So these are the main subtasks, and keep in mind, I've given you the definitions on a very high level. I haven't gone into depth about implementation. Moving on, my fellow officer Shreyas is going to take over.
Yeah, thank you, Ashwarya. So I'll be explaining one of the projects I've done using text classification. But before I do that, I want to just go over like the few different types of applications of NLP. So NLP has like two major um, applications, which are speech classification, which is used in like Google Translate, and text classification, which is used to like do topic labeling, which is what my project's about. So in my project, I created an NLP based and machine learning based software that automatically detects the topic of a sports article using an article's text. And I used the Stanford Core NLP's library to do so. And so, for example, if let's say I got an article which was about like the NBA playoffs that are happening right now, my program or project would detect that topic of the topic of like that article to be basketball. So to do this, I extracted like features from the sports articles, and these features are nouns and verb phrases, which are like a structured data from these sports articles. And I would get these noun and verb phrases from first parsing a sports article and separating the sports articles, the text into different sentences. And then I would separate each sentence into its tokens or each word, as Ashwarya was talking about. And I would use the parts of speech taggings, which are pause tags, and grammar relations to distinguish the different noun and verb phrases. So if you look at the image on the top right, for this sentence, the quick brown fox jumped over the lazy dog. It's each word is its own token, and it's been um, separated from each other, and each word has a part of speech tag associated with it, such as like the has DT, which is an article, quick has JJ, which is an adjective, and same with brown, and fox has NN, which is a noun, and jumped has VBD, which is a verb, and so on. And I would use these parts of speech taggings as well as the grammar relations, which is in the basic dependency part of that image, where I would use the different relationships between the words to categorize different noun and verb phrases and use that as input to my machine learning algorithm. So for example, in this case, if I had this sentence as an input to my program, I would have quick brown fox, jumped, and lazy dog as inputs to my machine learning algorithm. And just a brief overview of like my project used with the NLP and machine learning part is that I would use the label or the topic of the article as input to the machine learning model, as well as the input text, which would be converted into its features, which were the noun and verb phrases. And as I got more and more noun and verb phrases and labels together into my machine learning algorithm, it would start being able to predict different the labels of different features, and it would create a classifier model, and I would use that classifier model to predict the label or the topic of different articles. And here on the bottom of the slide, I have a link to my project, which is just like a HTML like page where where you can check out the different topics of sports that I've categorized, and you can click to see which articles I've used as training and test, and you can check whether my machine learning project or machine learning model classified that article as its category. And next slide, yeah. And so this is just like a overview, just a basic overview of my project. So I would convert the raw text into not technology, sports, and fashion, but just different categories of sports articles. And in my case, I had 10 categories of sports, such as having like basketball, soccer, football, etc., and other, to have like articles that weren't any of the 9 topics. And I would use like in the next photo, it's just like a basic idea of feature extraction from a text. So I would split the text into its different sentences and then split those sentences into its tokens. And then I would use those tokens to check to see how many times each of those tokens were used in a given sentence or article. And I would use that as input to my machine learning model. So there are several different Python tools that you can use for natural language processing. So one example would be the Stanford Core NLP library, which I've used for my project. And this is originally written in Java, which I coded in Java for my project, but it's also available in Python and JavaScript and a ton of other languages. And this is a really good option if you want to get or use the grammar relationships or grammar analysis of like different words or different sentences to get the relationships between like each noun or each adjective and those relationships. And some features that the Core NLP library has to offer are parts of speech taggings, entity recognition, tokenization, and splitting sentences. And the NLTK library is one of the most widely known NLP libraries for Python. And this library is super useful for making like computational logistics super easy. And some features it offers are classification, tagging, parsing, and semantic reasoning. And the final Python tool I'll be explaining is Spacey, which is a Python tool or NLP library, which is super useful for extracting or working with large-scale information extraction tasks. And some key features it uses are parts of speech tagging, tokenization, dependency parsing, entity recognition, and methods for cleaning and normalizing text. So yeah, thank you guys so much for your time, and let us know if you have any questions.
Awesome. So yeah, that's all for our presentation today, guys. Thank you so much for coming. Just a heads up, now that we're done with the presentation, the remainder of the next 10 minutes will be for Q&A. And if you guys are interested in our next meeting will be an intro to Python workshop. And we'll also be having an application where we'll be applying the linear regression algorithm as well. So we're going to get started on introducing some ML algorithms. And then moving forward, the next workshop will be an intro to CNN. So be on the lookout for our emails, and we'll make sure to keep you guys posted as to what to expect from there. Sweet. That should be it. Thank you.
Thank you all for coming today.
Does anybody have questions? Of course. Glad you liked.
Hello?
Hello.
Hi. So yeah, I had a question. I'm studying cybersecurity, so this is really interesting to me. Email spam detection. Can you guys maybe go over how this is done again? Because yeah, I was kind of interested in that.
You said email spam detection?
Yeah, like checking to see if an email is phishing. Like, how would that be done automatically? Like, how would you teach a machine to learn to check for phishing?
So if
on a broad view, okay, like on a broad view, it's like the algorithm goes over the text, it also involves NLP, where it goes through the text of the email. So the phishing emails would generally have like some kind of pattern where like they would be giving some offers or awards or something. So based on those features extracted, then there's like a classification layer where it's like trained on like both phishing emails and non-phishing emails. So it's trained on that, and whenever a mail comes in real time, we extract the features, and then that's how it predicts it. I mean, that's a brief overview of how it works.
Yeah. Okay. Thank you. Yeah.
Uh,
So yeah, no, that's kind of a large question.
no worries.
Yeah, that's a very broad, but yeah, that's the general idea.
Thank you.
We also have a follow-up question by Sai Krishna, who's asking, could you explain the breakdown of the process neural networking using the dog as an example? What components does it compare during the hidden layers? Anyone want to take that one? Ava, was that your example?
Yeah, I mean, so basically kind of like what I said, like when it takes an image and it compares, so it's looking for lines and shapes. And so that's why it uses the light and dark contrast. And so like in the instance of like a dog, I guess, image versus like a cat, it would have been using that shaping and that mapping to like determine what shape it's looking at and then how that shape matches with a dog shape or a cat shape based on like a bunch of other images that it like already knows. And so I think, does that help at all?
Yeah, but what does it do when the customer realizes that it's wrong? How does it correct itself?
So that's when I guess when it's like told it's wrong, it's kind of like how everyone was saying how like when it's counted as like a yes or a no, it would then count that like run and that prediction is like wrong, and it would know to go back and like if it were to try to like do something similar again, it would know that that was wrong.
So there's a
So,
like
how
back.
would you expect it to update its database of the comparison resources that it already has?
If you want to do this a supervised method, you can, and you know for a fact that it is wrong, you can go and set that as wrong. If it guessed cat when instead of say dog, and you know that, and then you just keep iterating that. That is one way that you can get it to correct itself.
Does anybody
Thank
else?
you.
Of course. Does anybody else have any questions? Officers, if I can get you to stay after the call. If you don't have any questions, you're free to go.
I had one more question. This is kind of another broad question, but it's more of like a hobby thing. How do you get into like? Because I'm really interested in AR and VR stuff. How do you get into that like as a hobby?
AR and VR.
So I can somewhat answer this. One way is, what grade level are you in?
I'm basically senior year.
Okay, so you'll be starting your capstone soon. My personal capstone this year involved doing a VR interactive airspace simulation for air traffic controllers.
Wow.
So one way that there's going to be a lot of VR projects for each year's capstone, and that is one good way to ease yourself into work in VR or working in, let's say, Unity in order to create VR applications. Aside from that, you can also do it on your own, which is a bit more difficult because you won't necessarily have a existing project. But there's a lot of good Unity tutorials in order to make environments and scripts that help with interacting and creating VR.
Cool. Thank you.
You're
Yeah, I
welcome.
would like to add on to that. So my capstone also involves augmented reality stuff. So I'm taking a course on Udemy, and I think they have really good courses for augmented reality and VR. And I think there's a course that's completely project based. They teach you like around 11 projects or something in one go. So you should definitely try and look into that too.
Yeah, I'll check that out.
Great, cool. Does anybody have any follow-up questions, or if not, you guys are free to go.